Is FE Peer Review. The date is the 10th of November 2023. Eddie, also known as Flat Earth Banjo, needs to learn his tools. In this video, we're going to look at a bit of the work of Eddie, Flat Earth Banjo, but I wanted to give a shout out and thanks to Hugh Jarsz. You probably all know him already and know his channel, but if you don't, I encourage you to head over there. You'll find a link in the description. He just put out a video doing a full detailed review of each of Eddie's studies, we should call them, I guess. Eddie has been focusing on taking flight paths of flights that had emergency diversions and looking at where they diverted to. He's then been tracing these paths onto maps and trying to use this to build a case that the Earth is flat based on these diversions. He is using a Gleason map as his flat Earth map, and we'll discuss that. He is using Google Maps as a comparison for the globe model, which we'll discuss that as well. I'm not going to get into the details of his flights that he's looking at. That I want to refer you to Hugh Jarsz and his recent video, because he goes into every single one of them and shows in every case how Eddie is misunderstanding or misusing his tools and is wrong. I want to focus a little bit more on the tools themselves. So we have the Gleason Flat Earth map. Here's one. That's one of the things we're going to look at. Something else we're going to look at is the Google Maps. Here's an image of the path from Beijing to Dallas on Google Maps, and I've chosen that because it just so happens that on the Hugh Jarsz screen that I froze on here, it was a flight from Beijing to Dallas that Eddie was looking at. So I've got Google Maps, Beijing to Dallas, and I've got Google Earth, Beijing to Dallas. And then we've got our Gleason map. And there's our Gleason map. And let's start there. And in fact, I'm going to make a little detour myself here for a moment. I've done a number of videos on map projections, and I've been really enjoying doing those. So I think I'm going to go back and do a few more. And my next video will probably be one looking at the map projection that is the basis for the Gleason map. It's called the azimuthal equidistant map, and I think we all would enjoy getting a good look at it. If you're a flat earther who is looking for a map, and this is one that's commonly pointed to, you will also find that Gleason, that azimuthal equidistant map projection video that I'll be doing next. Interesting. So for a start, Eddie. This is not a flat Earth map. Literally the Gleason map itself. If you look at the actual Gleason map, and we have a nice picture of one here, and it's even still got its original little measuring stick in the center here. It's a nice example. It says at the top, New Standard Map of the World. And then it says just underneath, in fairly large letters, on the projection of J.S. Christopher, Modern College, Blackheath, England. I don't remember the date. It's probably on here in fine print somewhere. It was probably the 1890s. I don't remember exactly. Anyhow, it is a projection in its own word right there in the title on the projection of J.S. Christopher. So that means that it is a projection onto a flat surface because we are looking at a flat surface. So it's not a flat Earth map. It's a projection of a globe onto a flat surface. It says it right there on the image. So Eddie, you don't have a flat Earth map. The comparison that you want to do, which is a perfectly valid approach, needs to have a flat Earth map to work with. You can't do your comparison without a flat Earth map, and you don't have one. So you can't really even start doing your flight comparisons until you get a flat Earth map together. Now, that's a fairly involved project. I'm not saying that you need to map every single spot on the planet before you can do anything else. But it's going to involve some work. And it's more than one person can take on. There are a number of flat earthers in the world. You could join together. You could have joined together years ago, I should point out, to do this. And I've been asking for years why it's not being done. while you guys aren't working on it. You keep claiming about flat Earth, but you don't actually make an effort to create a flat Earth map. What you'd have to do, I will give you an example here. There's the United States. We'll start with the continental United States. Now, the challenge you face is you need to cover a large enough area that you can show a meaningful difference between if the surface were flat versus if the surface were the exterior of a sphere. Take this scheme. Starting in San Francisco, you have a distance to New York City. You could pick a nice convenient landmark in San Francisco, and I'm going to suggest airports since we're talking about flights. You've got an airport in San Francisco and the San Francisco International Airport, and then you've got JFK at New York. You've got an airport in Miami and an airport in Dallas, and then back to San Francisco. Or better yet, San Francisco, New York, Miami, San Diego, and then back to San Francisco. That gives you 4 lengths that you guys could measure. You could determine the distances, and then you could also determine San Francisco to Miami and New York to San Diego. And that network, that net of distances, will either fit on a flat surface or it won't fit on a flat surface. If it doesn't fit on a flat surface, you can get an idea what kind of a surface it's fitting on a number of different ways. But the point is you will have ruled out a flat surface. So if you were to do that on the lower 48 states in the United States, and you get one of your flat Earth friends from Australia to put together a group of guys down in Australia and do something similar, you could cover a continent-sized space on Australia, and then perhaps you can draw up some people in Europe as well. I should think, Madrid, Athens, Stockholm, London, something like that would make a good set of 4 points. If you were to do that, you would actually have the beginnings, the adequate beginnings for a world map. And if the Earth is actually flat, you'd have an adequate beginning for a flat Earth map. So that's what I'm suggesting that you guys need to do. But you can't just take a map projection like the Gleason, which is based on projecting a globe onto a flat surface, call it a flat Earth map, and then use it for comparisons. That just doesn't make any sense. It's not a flat Earth map. If you want to claim it is a flat Earth map, then you're going to need to test it. So how would you test it? So how can we test it? Well, we want to figure out if it's an accurate to-scale map. And to-scale means one linear scale that works across the entire surface of the map. For example, we might have a linear scale of 1 centimeter equals 100 kilometers. So if I put a centimeter ruler down on this map and it gives me a distance of 100 kilometers here where I've got the mouse, and then if I put it over here in Australia and I get 100 kilometers, needs to match. So I could take 2 points, say I put my scale down on the map on the United States and I measure 1 centimeter, 100 kilometers. I then check those 2 points on the actual physical Earth, planet Earth here, and see if they're 100 kilometers apart. If the answer is yes, great. Now if I do that again over here in Australia, put my 1 centimeter scale down on the map in Australia, and I find 2 points in Australia. I go and find those actual points in the real Australia, measure the distance, and they're 100 kilometers. Great, everything's looking good. We've got a consistent linear scale across the map. So that would be a way to test this map. Well, I'm going to show you a close-up of this area, and let's see what sort of results we start to get. So I've zoomed in here, and we've got down at the bottom center of the screen the United States, and up top center, just left of center, we've got Australia. And you'll see that there are 2 red lines. There's a red line across the United States, and there's a red line across Australia. The one in the United States goes from San Francisco to Cincinnati, Ohio. And the one in Australia goes from Sydney to Perth. Now let's go over to Google Earth and take a quick look here. Sydney to Perth. Straight line from Sydney to Perth, according to Google Earth, if it's accurate, 3,310 kilometers. Can we remember that? 3,310. Now we're going to scoot on over to North America. And we're going to go from San Francisco up to Cincinnati. 3,280. Okay, let's go a little bit farther. 3,310. We're in the suburbs of Cincinnati over here. So those two pairs of cities, San Francisco to Cincinnati and Sydney to Perth, are approximately the same distance apart, within a few kilometers, within about 5 or 10 kilometers. They're the same distance apart. If we look at our map here, our Gleason's map, are these two red lines the same length? We see that they're not. I'm going to move that San Francisco to Cincinnati line over to Australia here so we can compare it side by side with the Sydney to Perth line. I think you can tell that they are quite a bit different in length. I don't need to make them line up. Should be pretty obvious. So what we see is that the Gleason map does not have a linear scale. The same distance on the ground, 3,310 kilometers, is a different length on one part of the Gleason map compared to another part of the Gleason map. This is not a two-scale linear to scale map. The way the Gleason map is set up, it's called an azimuthal equidistant map, and I'm going to show you another example of one. This is the Wikipedia page on azimuthal equidistant projections, and we see the base for the Gleason map in the image on the top here. And we see that, as they mention here, it's actually the map that's used by the United Nations in their logo. Here's a closer view of it. And what we find with the equidistant azimuthal map, the word equidistant meaning equal distances, is because this map sets the longitude lines, if you follow a longitude line, you'll see it crossing latitude lines. And those are equally spaced. That's the equidistant. The spacing of these latitude lines is equal. So if you follow a longitude line and you go from, I'll put the mouse up here at the top where you can see it more clearly. You go from this point to this point. You've traveled the same distance as if you went from this point to the next and from this to the next. So that's the name. That's how this map gets its name, equidistant azimuthal map. So if you were to use a scale to measure along north-south lines, along longitude lines, that would be equal, that would work. You'd get consistent linear scale on any two points if they're on the same longitude line, if you're measuring straight down the longitude line. But if you start measuring across latitudes, then you're going to find that this map, it does not have a linear scale. And if you start measuring across, it doesn't have a linear scale either. It only works linearly if you follow a longitude line. So this map and the Gleason map are not flat Earth maps. They are projections of a sphere. So back to my earlier point, Eddie, you don't have a flat Earth map, or you're not using a flat Earth map anyway to do your comparisons, and your comparisons are kind of meaningless in that respect until you've got a flat Earth map. So first order of business is to get yourself a real flat Earth map and test it. Because when you start doing the comparisons, the first thing we're going to want to do is test your map and make sure that it actually matches the planet here. The distances actually work. Eddie, the next point I want to cover has to do with the idea of the great circle and what it is. In essence, a great circle is the shortest path between 2 points on the surface of a sphere moving across the surface of the sphere. A quick and easy way to find one is simply to get a desktop globe like we see in the picture here and a piece of string, and put one end of the string at your starting point and the other end of the string at your end point, and then just kind of gently nudge and tug on the string until it's as taut as you can get it and as short as you can get it. That is the great circle between those 2 points. Now there's lots of complicated math that you can use as well, but in order to just understand it conceptually, I think this photo here gets the point across. So when airlines plan flights, in order to save on fuel and reduce cost and save time, they try to use great circle routes because these routes are the shortest distances. So there's sometimes reasons why they have to diverge from that. There's restricted airspace on military installations that you can't fly over, or perhaps there's a big storm and for the safety and comfort of the passengers, they decide to go around the storm. So there's reasons like that why they might diverge from the Great Circle, but generally they keep pretty closely to it. Well, when you're doing your comparison, looking at those emergency diversions on those flights, you weren't comparing apples to apples. You weren't using great circles for your globe examples. I'll go back to that image we started with here. What we see on the screen here is, on the bottom part of the screen is kind of cut off, but you were looking at a flight that started in Beijing and ended in Dallas, and it ended up due to an emergency, having to stop, I don't remember, Anchorage or somewhere. Anyway, we see on the bottom of the screen the starting point of it on the Gleason map, starting in Beijing and going down the image. And on the top picture, we see it on Google Maps. And this is the point I want to make clear here. This is Google Maps. This is not Google Earth. And this is one of the reasons why I think you have a misunderstanding, Eddie, about your tools. You see, Google Maps doesn't show you a great circle route. It just simply shows you a straight line. It just draws a straight line on the screen between the 2 points. If you want to actually see the great circle route, you need to go to Google Earth, and I'm going to bring that up now. So there's Beijing on the left, and there's Dallas on the right, and the great circle path is this line here. And it is going all the way up over northern Alaska. Whereas if you look at the image on Google Maps, and I have a Google Maps view here. Here's the Google Maps view. You can see that Google Maps does not draw that line in the same place. It draws it as coming down here somewhere. That would not have been the flight path that flight would have taken. It would be more like what Google Earth showed, which was up over northern Alaska and coming back down that direction. Now, if I can find a flight on Flight Radar, I will add that in here. And that will show you that there are actual flights following these actual paths, and it's not just lines on a screen. So I'm going to go and take a look for that. Well, we're looking at a Flight Radar now. This gives us actual flights that are in the air at this moment. Eddie, if you're not familiar with this website, you'll probably find it very interesting. I'm not finding a Beijing to Dallas flight that's actually in the air as we speak, but I'm finding a few flights that are related. Might be useful. So here's a flight that originated in Los Angeles, where I'm circling the mouse, and it followed a great circle route, and it's coming down in China, Xiamen, Los Angeles to Xiamen. So we see that it went well up into Alaska as well. I had mentioned that the Dallas flight flew across northern Alaska. Well, this one coming from Los Angeles is a little bit further south, which is not too surprising. There's also another flight here, JFK to Tokyo. We see how far north that goes as well. That's going all the way up into Alaska and coming down in Tokyo. So there's a couple of examples of similar flights that are in the air at this moment as I'm making this video that followed great circle routes, which took them all the way up into Alaska. That covers the main points, the two main points I wanted to address to you, Eddie. And that's that for a start, in order to do a comparison like you're trying to do, you need to have an actual flat Earth map, not a globe Earth projection. And second, I wanted to clarify this business about what is a great circle and that Google Maps does not give you great circles. You need to look at Google Earth to get great circle routes. So in the future, once you've got your flat Earth map, you want to do the comparison, you'd be better off looking at Google Earth rather than Google Maps. I should say that I'm doing this on a desktop, and I understand that Google Maps and Google Earth may possibly work a little differently if you're working from a mobile phone. So I can't say how it works on a phone, but on a desktop, what I'm saying is correct. I'm going to add one more quick little tidbit here, and I don't want to distract from my main points that I just mentioned. But Eddie, this is something else that kind of fits into the research you're doing and something that you might want to look into, and that is long-haul flights in the Southern Hemisphere that start and end in the Southern Hemisphere. It used to be there weren't very many commercial flights like that. There are a few more now. You can track them on flight radar. I don't see any in the air at the moment that are doing like from Australia to South Africa or Australia or New Zealand over to Argentina, but they do happen 2 or 3 times a week. They're not every day. So I encourage you to do a little research and find some of those flights and watch the paths that they take on flight radar. Now, I actually did a video last year, about a year ago, where I watched and tracked some of those. YouTube's most boring video, tracking transoceanic Southern Hemisphere flights. Let me jump ahead here. So I've skipped ahead here. I'm at the 22-minute 40-second mark, and this flight originated in Angola and was headed to South America, Argentina, and it's just about at the end of its flight here. You'll find several flights on this video. If I remember right, I did more than one. I think I did 2, at least 2. You can get the flight schedules and the airlines off of this video, and you can maybe take a look at that on flight radar yourself, watch it real time, and look at the paths they're taking. If we look at paths in the Southern Hemisphere, if we look at great circles in the Southern Hemisphere, let's take that one from Angola to Argentina. Luanda's up here. Let's get a line from Luanda. There's Luanda to Buenos Aires. And that would be the Great Circle route. You might want to find some of these flight paths on Flight Radar and Google Earth and check them out on the Gleason map. Or if you can get your actual flat Earth map put together, check it out on that. Anyway, this video is going to be long enough, so I'll close it here. I want to say thank you to everybody that made it this far. Stop by Hugh Jarsz and see what he's up to. And do remember to give this video a like, and if you haven't subscribed, it's always nice to get some new subscribers. So that's all. Have a great day, and I'll talk with you again soon. My next video will be one of my map projection videos, probably on the Gleason map. Okay, take care everybody. Bye-bye.